Okay. So last class we did the differential equation method of solving the harmonic oscillator problem. It was a long derivation and it involved a lot of mathematical results. Uh, and then finally we arrived at the set of energies, which was the same as what we got in the operator formalism. But our wave function didn't quite look the same. So we have one. Okay. So what we got from the operator derivation of the harmonic oscillator was, after so I showed last class, I guess I did convert the a dagger form of the psi n to the differential form. Yes, I did that. So what we got was this. So this came from the operator formalism and from the differential equation solution. We got the wave function to look like this. Okay, where Hn were the set of Hermite polynomials. Now, I mentioned that there is the Rodriguez formula, which tells you that the Hermite polynomials can be written in a interesting way. So I'll use that here. And so I'm writing Hn now, okay, as minus 1 to the power n, e to the power xi square, dd xi to the power n, or minus xi square by 2. No, 2. Okay, by xi square. Okay, so what we then need to show in order to prove that these two are equivalent is that this expression xi minus dd xi whole to the power n acting on e to the power minus xi square by 2, that is the same as this part. So the rest is the same. Yes. No, did I? Okay, I can simplify this one more step. So before I do that, I'll write one more step. So this part can be simplified. So 1 by root over 2. So this is minus 1 to the power n, e to the power xi squared by 2, dt xi. Yes.
Ma'am,
Yeah.
the part which you've written that in place of the Hermite operator, right?
The Hermite polynomial, yes. So this is
Hermite
the
polynomial. But ma'am, last class actually you had told that it should be e to the power minus xi square by 2.
mm, oh yeah, it is xi squared by 2, is it? Wait, last class I had said xi square by 2. Just 1 minute. Let me just verify that. No, not this one. So I need the Rodriguez formula. See, when I have to look it up. I don't expect you to be able to write everything. So this is the no. I had written xi square by 2, then that was a mistake. It will have to be xi square. Sorry. Oh, you mean this one? No, this is xi square. I made a mistake last time. So you can correct it. And I'll upload the corrected notes also. Okay. Yeah. So this is what we need to show. So let's do that. So what I need to show is that. So instead of xi, I'll start writing y now because I'm finding it very difficult to keep writing xi all the time. Okay. So this is just identity. So it doesn't matter whether I write xi or y or whatever. So I need to show that is equal to minus 1 to the power n e to the power y squared by 2 dy to the power n e to the power minus y squared. Okay. Now we will do the proof by induction. So first we'll try n equal to 0. So for n equal to 0, the left hand side is equal to simply 1 into e to the power minus y squared by 2. And the right hand side is equal to again. So minus 1 to the power 0 is 1. Then you have e to the power y squared by 2. And then derivative of, so there is no derivative. So you just have e to the power minus y squared. Power minus y squared by 2. Okay, so this is fine. I can show it for n equal to 1. Then the left hand side is equal to y minus dy to the power minus y squared by 2. And that is equal to y into e to the power minus y squared by 2 minus 2y by 2 to the power minus y squared by 2. Okay. So this is 2y e to the power minus y squared by 2. Okay, then let's do the right hand side. The right hand side is equal to minus 1, so there's a minus sign. Then e to the power y squared by 2. Then d dy of e to the power minus y squared. And that is equal to that is equal to 2y e to the power minus y squared by 2. Therefore, LHS equal to RHS for n equal to 1 as well. So what is the next thing that we need to show? So assuming that the equality holds for n equal to n, we need to show that it holds for n equal to n plus 1. Okay. So assuming the relation holds
I mean,
for,
you need to do n equal to 1. You could have just started from 0 itself.
yeah, you could have started from 0, but you could have started from 0. Just 0 was fine, but I just wanted to show you that it's simpler to just put in the value of n also. Okay, holds for n, we need to show it holds for n plus 1. So the left hand side for n plus 1 is y minus dt whole to the power n plus 1 e to the power minus y squared by 2. We'll work with the right hand side. Okay. So what we will do here is we will factorize it into the part which depends on n and the rest. So from minus 1 to the power 1, we get a minus sign. Okay. And then we have e to the power y squared by 2. And from the dd y part, I separate one dy. Okay. And I'm moving the minus 1 to the power n, which we had left inside. Okay. Then ddyn, this is what we have here, e to the power minus y squared. Okay. Now our target is to get e to the power plus y squared by 2 over here, you see. So what we will do is we will introduce a e to the power minus y squared by 2 into e to the power y squared by 2 over here. So we will do this. E to the power minus y squared by 2 or plus y squared by 2. Y squared. Wait 1 second. So I had minus y squared. Is it? So my right hand side had a minus y squared. Okay. Fine. So then we can call this quantity, which is basically this is basically the right hand side when we have the relation for n equal to n, right? So we can write that as the left hand side, and the left hand side for n equal to n is y minus dd whole to the power n e to the power minus y square by 2. Okay. Then we call this function, this part of the expression, as a function fy. This is just to make it look short, okay, because I want to do the derivative. Equal to minus e to the power. Oh, I made a mistake here.
It should be plus y square.
Yeah, plus y square. Yes. Okay. So dy of e to the power minus y square by 2 into f. Okay. Then I can do the derivative. So first I take my f out and do the derivative on the exponential. That gives me minus 2y by 2 e to the power minus y squared by 2f. And then we have the next term where I take out the minus y squared by 2 and I do a dty on f. Okay. So this is now, oh, sorry. Already have the f. So let's, this and this cancel. So we have yf, okay, and this cancel. So I have minus df dy. Okay. So that is equal to y minus dy acting on f. Okay, acceptable. So then we have y minus dy and f is y minus dy to the power n e to the power minus y squared by 2. So this is equal to y minus dy whole to the power n plus 1 e to the power minus y squared by 2. Now this is the left hand side that we wanted. So this is equal to left hand side. Sorry. This is equal to left hand side. Hence proved. Okay. So we showed the operator identity. And then if you put it back, of course, here, then we show that the two excited state wave function, the general form of the wave function obtained from the operator formalism and from the Hermite polynomial solution, they are the same.
On that A, if I don't know that symbol, that script letter minus D by D script letter, that is the A dagger operator.
Oh, no, I showed you how to get that from the A dagger last time by writing the A dagger in terms of the momentum operator.
Yes,
So,
but that is the, I mean, that y minus dy, y minus d dy. This
yeah. That comes
that
from
is
the
A
A
dagger, right?
dagger. Yeah. So this is what we did last time. So in case you've forgotten, you can have a look. So this is from last class. So if I write A dagger in terms of the momentum operator, and then I go over from the x to the xi as we defined in the during the solution of the problem, then we get this expression. And then we show that you can express this xi minus dd xi as also just dd xi to the power n, like in the Rodriguez formula for the Hermite polynomial. Okay. So this is, yeah. So then let's continue with some more. So this is the equivalence now. And so now we'll do some properties of Hermite polynomials. Oh, and one more thing. So someone asked me the about the getting explicit excited states from the operator formalism. So there you do not necessarily have to come to the Hermite polynomials. All you need to do is write a dagger in terms of P and actually carry out the operation of P on psi 0. Okay, so that itself will give you the various excited states directly. Okay. They will not look exactly like the. No, I think they will. Sorry, they will not look exactly like the Hermite polynomials unless you do the 2 to the power n division. But other than that, it will work. Okay. Then some properties of the Hermite polynomial. Let's see. So there are some interesting things. So one is the recursion relation. So an n plus 1th order Hermite polynomial that can be written in terms of two simpler Hermite polynomials. So it's 2 xi hn xi minus 2n h n minus 1 xi. You can try with some typical Hermite polynomials to verify this. So this is something you can be asked, for example, in a test or something, that you verify this relation for some h2 or h3 or whatever. Then there is a simple rule to differentiate Hermite polynomials as well. So if you differentiate the nth order Hermite polynomial, you simply get 2n times the previous. I don't like this. What happens? Okay. You simply get 2n times the previous Hermite polynomial. So you don't necessarily have to carry out the differentiation. Okay. The third thing, which is, well, not so useful to us, at least I haven't used it, but just so that you are aware, the Hermite polynomials are also related to a sort of to an exponential function in this manner. So you can write an exponential of this form in terms of a series of Hermite polynomials. So this can be useful at some point, but not directly in this course. Okay. Fine. So now, these are just some bits and pieces of information. But now we'll do something quite interesting. So, we'll talk about tunneling. So you must have heard about quantum mechanical tunneling, which means basically that the wave function can spill out of the potential well even when it is infinite.
Ma'am?
Yeah?
Ma'am, could you just scroll up a little?
Yes.
Yeah.
Okay.
Thank you, ma'am. Done.
Okay. So the next thing we'll do is we'll try to find out the probability of finding a quantum particle outside the potential well. So what does that mean? It basically means that if I draw my harmonic oscillator potential as, it's very difficult to draw on a tablet. Okay. Say it looks like this. Then you have the lowest energy level at half h cross omega. Then you have equispaced energy levels, remember, half h cross omega. And now I will plot psi n x versus x. And then you'll see, if you do the calculation actually, then it looks something like this. Then you have, okay, this is looking bad, but like this. So the wave functions, they range from minus infinity to plus infinity. The tails look like e to the power minus u squared, remember, or e to the power minus x squared. I've forgotten exactly what the factor was, but so it basically extends to infinity. But my potential well does not, I mean, it is, for each energy level, it has some sort of limit. But the wave functions go from minus infinity to plus infinity. So it appears that the wave functions spill out of the potential well. So this had not happened, for example, for the particle in a box.
Ma'am, the total energy is given by that line you're drawing, but not the potential, right? That is still extending till infinity. I mean, my cake, half cake square.
So what I mean by extending to infinity is, yes. So this parabola has a range which goes up to minus infinity, yes. But the energy of the particle, it follows these levels, right? And that is
Yes,
related.
ma'am, that is the total energy, right?
Yeah, that is a total energy of the particle. Yes. So that is. So classically, this would not happen. Classically, if you have an actual potential well like this and you put a particle in it, it would stay in this region. I mean, it cannot go out because it encounters a barrier when it comes to this wall. But in the case of quantum mechanics, our wave functions are, for the harmonic oscillator, they go up from minus infinity to plus infinity. So they spill out of the potential well. It's a little tail, but yes, they're outside.
Do you mean to say that if we write E as half kx square plus half mv square, so when the line is intersecting the parabola at that point, half kx square equals E. So if we go a little bit above that, then kinetic energy would need to be negative to overall make it equal to E, something like that.
So for a classical particle, when it encounters the potential wall, its kinetic energy would have to become zero because it would be reflected off the wall. So it would never have enough energy to cross this wall.
Okay.
Yeah.
Ma'am,
Yeah.
ma'am, are you actually? I think that it would be better if today we just finish the oscillator portion and not enter into any new section, because actually many people so I think it would be better if we hold a question and answer session.
Okay, sure. Fine. I mean, we only have 20 more minutes anyway, so. So
Okay,
I'll
ma'am,
just
that's
talk
allowed.
about the physical parts of the harmonic oscillator problem. Okay, so let me, yeah, so the tail. So we can try to quantify this, for example, by finding out what is the probability of finding a particle outside the classically allowed region. Okay, so let me call the amplitude of oscillation. Let's just talk about the ground state maybe. Then I'll call the amplitude of oscillation A. I mean, this A is different for different states, but let's say this is A. Okay. And then we'll try to find out the probability of finding the particle beyond this minus AA region. Okay. So the ground state energy of this particle is then half m omega squared A squared. So this is at the point where we only have potential energy. Okay. So ground is equal to this. And energy is conserved. So the sum of kinetic and potential always has this value. Okay. But the potential is different across this whole range. So at this 0 point, you have only kinetic energy, and at the minus A and A, you have only potential energy. But the value is half m omega squared A squared. Okay. Then this tells you that A is equal to root over 2e by m omega squared. Okay. So if I say that my x lies between minus a and plus a, this is equivalent to saying minus root of 2e by m omega square less equal to x is less equal to root of 2e by m. Okay, so this is basically the classically allowed region. So what we want to find out is the probability of finding x greater than a, which is integrate from a to infinity mod psi n square dx. Okay. So we can do actually only one side if you like. And then when you evaluate this, you will get some sort of finite value. So if I put in the wave function for the first state, so let's say a to infinity, I can say psi 0 maybe. And that looked only like e to the power. Yeah, there was a factor into x squared dx. Now I forgot exactly what it was. It was m omega by pi h cross, but let's see which order. Okay, that's too small. So psi 0 was equal to root of 8. M omega by pi h cross to the power 1/4 e to the power minus m omega by 2h cross x squared. So this was the this was psi 0x. So psi 0x mod square means basically 1, this is half, and I can delete 2 from here. Okay, got it? Dx. And this is what is called a Gaussian integral. So you can use a standard integral form for this, and you get some value for this. So I'm not doing this, you can try it out. Okay, so since you all have some doubts, I'll take your doubts now then. I'll stop here. And you can tell me
So then
what...
we get e to the power minus 2m omega by h cross. We squared the wave function, right?
I squared the wave function. Yeah, so there was a 2 here.
Oh, okay.
Yeah, I removed that. Yeah. Okay. So tell me. So the harmonic oscillator problem is a bit tedious, I agree, both the operator formulation and the Hermite polynomial. But you have to understand it once at least to appreciate how quantum mechanics works. So, and I'm sorry it's too mathematical for those of you who don't come from very mathematical backgrounds. But the first part of quantum mechanics really does have a lot of mathematics. So yeah, so tell me.
Ma'am, I have a question. In the when we actually in the algebraic method, we got the quantization quite naturally. I mean, there was no need of approximation of such things. But in case of the analytic method, we had to take several approximations, right? So, I mean, why in one approach approximation is needed, but in another it is not? Why this is true?
So I guess when you say analytical method, you mean the differential equation solution?
Yes, yes, yes.
Yeah, okay. So no, actually it was not so much approximations. We didn't do approximations. What we did was we guessed certain forms, but afterwards we always allowed it to be anything. I mean, uh, for example, when we're talking about the this ansatz or the guess solution that we took, an exponential multiplied with a polynomial series, then that exponential part we got by guessing in a limiting case, approximate. But when we multiply it with an infinite polynomial series, we are again covering the whole function space. So it's not like we made an approximation there.
Okay.
Yeah, so it's so both solutions are exact. But the arguments are a little bit funny, I agree. I mean, what I myself was most uncomfortable with was was getting the ground state from the annihilation condition in the operator formalism. But once you see that it really works out, then you start to appreciate the fact that it gives you a very neat, uh, what should I say? A neat framework for handling the harmonic oscillator problem. Because if you're dealing with these Hermite polynomials, it's really clumsy. Okay. Wait, there is some.
No, but actually the reason why we get the energy quantization condition is exactly the same, right? That we want to be able to normalize our wave function. So in one case, we want, I mean, we are not allowing it to go below zero in one case, and in the other one, we want the e to the power minus x square type terms only. So both of the things are following from the same physical input, right? In both methods, I mean.
Not Not really. I mean, for the differential equation, yes, it's the normalization. But for the
I mean, for the annihilation operator, if we use the argument that if energy becomes negative, then it's not normalizable anymore. So it should stop at zero, right? Like I mean, the ladder.
there the argument is that the energy cannot fall below zero. It has
Yes.
nothing to do with the normalization. It's just that since the potential is like the minimum potential is zero, the energy cannot go below zero. That is the argument. And that gives me the ground state wave function. The normalization is still external. I mean,
No, ma'am,
going
because
over.
you were told that theorem that I mean,
Yeah,
it
but the
cannot be
theorem.
negative.
Yeah, it says it cannot be negative, but that does not tell you anything about normalization. I mean, even if it was.
No, if energy is negative, then you said that we will get that kind of upward parabola solution. So that will violate.
Oh yeah. That is an alternative argument. Yes, that is also an alternative argument for that. It will not be normalizable in that sense. So if you want to link it to that, yeah, but the quantization really did it. It didn't really come from that, did it? I mean, the quantization came from the fact that we saw that our step up and step down operators shift the energy by constant amounts or integer multiples of h cross omega by 2. So that was the quantization.
Okay.
Yeah, the annihilation condition just helped me to find out the ground state wave function. That did not tell me what the a and a dagger operators can or cannot do. So that was one thing. And then if you look like go back a lot and go to the, for example, the black body radiation problem, the first quantization problem, there the argument was a sort of related to boundary conditions, because then you started counting standing waves instead of all possible waves. That was the argument there. So that had something to do with boundary conditions, similar to particle in a 1D box. But then when you come to the harmonic oscillator, it's the normalization. And then when we do the the hydrogen atom, which is another painful derivation, that will, there again, the quantization is multiple. So it's here you only have one quantum number. In the hydrogen atom, you have three quantum numbers. And if I exclude spin, if you take spin, then four quantum numbers. And they all have different sources, and they're all have different arguments. So in when you do the mathematics for quantum mechanics, the quantization is I mean, it doesn't have the same source. It would be really nice if someone could have some quantum mechanical framework, mathematical or otherwise, with operators or whatever is or something entirely different, that allowed you to tackle all the problems in a similar way. But sadly, that does not exist as of now. So people, there are these basic ones which you study now, which are very different from each other. And when you do a research problem, you will use modified versions of these or combinations of these. So that is how it works.
Um,
Yeah.
Ma'am, actually, does this harmonic oscillator somehow describes particles, or I mean particles in a bond or such things, or just
Yeah.
it's just a completely mathematical experiment?
No, no. This the harmonic oscillator problem is a very useful problem. So it tells you about the vibrational spectra of molecules. It's related to the rotational spectra. So in your syllabus, you'll see there's also something. It also says you should do the rigid rotor problem, which we will not do because we don't have so much time. But that would give you the rotational spectra of molecules. So it's the harmonic oscillator is very very useful. It's also useful um, for particles in fields. So modifications of this harmonic oscillator problem will tell you how a particle would oscillate in a magnetic field, or a charged particle would oscillate in a electric field, and things like this. So it's very, very realistic. In fact, the particle in a 1D box and all that, those are a little less useful. But even those are used a lot in solid state physics when you're talking about excitations in a solid and things like this. So they consider the fact that the electrons are trapped between nuclei. So you have this particle in infinite wells, or many particles in infinite wells and all
Okay,
that.
ma'am.
Yeah.
Thank you.
Okay. Yeah. So it's almost 6 o'clock. So if there are people who really find this difficult, I can only tell you, give you one assurance that the exam questions will be easy. It will not need you to uh, work out lots of mathematical things. I mean, the assignments are, like I said, I want the assignments to be a bit more difficult, but that is not the level of your quiz. I mean, quiz or exams. I guess you saw that. I mean, the quiz questions were not terribly difficult. Maybe one or two, because I have to give a few difficult ones for the people who are really ahead in this. Okay, but you don't have to learn up the whole derivation. I'm just that is what I want to tell you. Just understand the arguments. Okay, so it's almost 6 o'clock, so I'll stop the recording.